Hello, we're going to continue our lecture. So we'll go through an example of solving a perpetuity, and then we'll move on to growing annuities, growing perpetuities, and lastly, amortization. Okay, so in example two, remember we stated that an example of a perpetuity is a loan that you just roll over but you never pay off. So let's try to figure out an example closely related to that. You've taken out a $500,000 loan. You will never pay back any principal on this loan, but you will always make interest payments of 8% per year. Suppose you get a tax credit of 40% of your interest. This means that the government gives you back 40% of the interest that you pay out every year. We want to know the present value of all your tax credits. Assume your discount rate is the same as the cost of debt, which in this example was 8%. How do we set this up? First, we want to know how much we pay out every single year in interest. So we take our 500K and we multiply that by 8%. 500K times 0.08 equals 40K. That 40,000 is the amount of interest that we pay every single year. We also know that we get a 40% tax credit, meaning that 40% of what we're paying out, the government is going to give us back. How do we figure out that number? We take our 40K and we multiply that by 40%. 40K times 40% yields 16K, 16,000. So now we know that every single year the government gives us back 16,000, and that's based on the 40% tax credit for our 8% interest on our $500,000 loan. Our next question is, how do we value that? In order to value that, we take our 16K, that's our annual tax credit, and we treat it as a perpetuity because we'll do this every single year. 16K divided by 0.08 yields 200,000, 200K. Okay, let's look at growing annuities and growing perpetuities. A growing annuity is a stream of cash flows over a finite time period that grows at a constant rate G. So our numerator, every single period, those cash flows are going to grow by some rate G. If the growing annuity makes payments forever, then it's called a growing perpetuity, in which case we're going to value that as C divided by R minus G. You'll commonly see C divided by R minus G as referred to as a Gordon growth model. So you'll see that very often in valuations. Okay, let's do an example of a growing annuity. Your firm is considering a project that provides cash flows for 30 years. The cash flow in the first year is estimated to be 10 million, and cash flows are expected to grow by 5% per year for the life of the project. Suppose the project's cost of capital, so our discount rate, is 12%. What is the value of the expected net cash flows generated by this project? Here I'm showing you the answer directly because I want to make sure you understand how to set this up. So we've got our 10 million. Our 10 million is our C. How is that going to grow? It's going to grow at a rate of 5% per year. So that's this, our 5%. What's our discount rate? Our discount rate is 12%. We also want to be careful about our order of operations whenever we're dealing with an annuity or perpetuity. Meaning, we have our 1.05, so that's 1 plus G, divided by 1.12, that's 1 plus R. We first want to divide our 1 plus G over our 1 plus R. We then want to take this number and take that solution to the 30. So we do everything step by step. We then want to do 1 minus all of this and then multiply this by this number. So step by step, we want to build it out. When we do the math, we'll solve and get the answer that's there on the screen. A growing perpetuity. You plan to hold a stock in perpetuity. You expect the first dividend of $2.50 to be paid next year, and the expected dividend payments thereafter to grow at 4% per year. Your expected rate of return for this stock is 10%. What are you willing to pay for the stock today? You've got our $2.50, that's our C. That's going to be our cash flow or our dividend in this example. We know what our expected rate of return is. Our expected rate of return is going to be our discount rate. That's 10%. And we also know our G. Our G is 4%. So when we put it all together, we've got 250 divided by 0.10 minus 0.04. And again, we want to be mindful of our order of operations. Okay. Our second concept are going to be discount rates. The discount rate R need not be on an annual basis. You can base an interest rate on any time horizon, quarterly, monthly, daily, etc. Suppose that we have an annual interest rate of 12%. Well, we know that our quarterly interest rate is going to be that 12% divided by 4, meaning every quarter we're going to have 3%. If it were monthly, we would divide it by 12, meaning every month it's going to compound by 1%. We always want to be mindful to make sure that our rates match our periods. So if we have an 8% quarterly rate, we can always, or if we have an 8% annual, if we want to put that into quarterly, we divide it by 4. If we have an 8% annual, we want to put it to daily, we divide it by 365. You just always want to be mindful that your interest rates are lined up with the period over which they're compounded. We will typically be working with annual cash flows and annual interest rates, but again, you can have discount rates that are quarterly. So an easy thing to sometimes trip us up when we deal with this is that it's not only our interest rate that we need to be careful of dividing by that period, but we also want to make sure that our N, that our time periods reflect that frequency. So let's look at an example. We've got $100 at a 12% rate, semi-annual, compounding for 5 years. That $100 is our present value. Semi-annual, meaning that 12% rate, it's going to happen, we're going to cut that in half. It's going to compound twice over the year. So over the year, for the first half, we're going to get 6%, and then for the second half, we're going to get 6%. We also have 5 years. 5 years are 10 semi-annual periods. When we put it all together, we've got 100 multiplied by 1 plus 0.12, that's that 12% divided by 2. All of that is taken to 5 multiplied by 2 because it's 5 years semi-annual. So you just want to be mindful to make sure that your interest rates and your compounding, your time periods, that everything's lining up. We can also solve for interest rates. So suppose that I know I put in $1 and in 3 years I get out 2. What annual interest rate would be needed to double your money at the end of 3 years? In this example, we know our future value is 2. We know our present value is 1. We also know our N, our number of periods, is going to be 3. What we don't know is our I. We don't know our discount rate or our interest rate. So we can solve for that. Again, setting things up, we've got $2 equals $1 multiplied by 1 plus I to the power of 3. When I take my order of operations and do everything step by step, what do I have? I have $2 divided by $1 equals $2. I also have 1 plus I to the 3. Next, I want to raise everything to the 1/3. 3 to the power of 3 raised to the 1/3 equals 1. And 2 to the 1/3 is just me taking the cube root of 2. When I solve everything down and solve for I, I'm going to find that I equal 25.99%. I equals 0.2599. What's the big takeaway from this example? The big takeaway from this example is that whenever I have my future value and my present value and my N, I can always solve for my I. I can always solve for my discount rate. So when we put it all together, a firm is considering a project that will generate quarterly cash flows of $3 million for the next 15 years. Suppose that the firm's annual cost of capital is 16%. What is the present value of the project's cash flows? 2 things we want to be mindful of. First, this is definitely an annuity. It's an annuity that's going to last for 15 years. But there's a little trick here. The trick is that these cash flows are arriving quarterly. So 15 years is actually 60 quarters. And I know the firm's annual cost of capital is 16%. That 16% is really 4% per quarter. So when you solve, for example, for Part A and put it into your annuity formula, you want to be mindful of the 15 years being 60 quarters and of that annual cost of capital, that 16% being 4% per quarter. Let's look at Part B. Suppose the cash flows are projected to grow at 1% per quarter. What is the present value now? So in this example, we know that this is going to be a growing annuity. And when we set it up, we've got our 3 million per quarter. So that's that. We also have taken our 16 and divided it by 4. So that's 16% divided by 4. And we know that the project is going to grow at a rate of 1% per quarter. And again, we always want to be mindful of our order of operations. So here in the numerator, we've got 1 plus G, and in the denominator, we've got 1 plus R. We want to take this actual number, so divide 1.01 by 1.04, and then raise this to the 60, and then do 1 minus this number to yield the answer on the screen. Hopefully, when you solve Part A and compare it to Part B, you'll notice that the answer in Part B is bigger than the answer in Part A, as it should be. If the project's cash flows are growing at a rate of 1% per quarter, it should have a higher present value than if those cash flows aren't growing at a rate of 1% per quarter. Okay. Our third concept is going to be net present value. So the equation for NPV, I'm sure you've seen before. It's simply the present value of all the expected cash inflows and outflows associated with the project. So the NPV today we also have some cash flow, CF0. That's typically the cost or the cash outflow that we're going to spend for the project. We then have the expected cash flows over the life of the project, each discounted at the appropriate discount rate. One of the challenges that we'll face when calculating NPV will be determining that correct discount rate. And that discount rate is going to reflect the riskiness of the project. So what we'll do in the coming weeks is figure out how to calculate the correct discount rate. So we'll do this in our following lectures when we build out an efficient market and when we build out the CAPM. Another challenge in NPV is that numerator, finding the expected cash flow. So an investment decision in this course will almost always be predicated on the NPV decision rule. Meaning, if you know the NPV of a project is greater than 0, you should invest in the project. If there's uncertainty over those cash flows, then you really have to take the expectation of those cash flows. So one thing I'm going to point out when I go back to this slide, in that numerator, we have E, and then in parentheses, we have cash flow 1. That E is an expectation operator. In math and symbolic math, it's a way of us showing that it's an average. It's what we expect to happen because we don't know for certain if the cash flows are going to be good or if the cash flows are going to be bad. So let's do an example together. A firm is considering an investment that will generate cash flows for the next 2 years. These cash flows depend on whether the market conditions are good or bad in each year. So in year 1, if the cash flows are good, firm's going to get 20 million and then 30 million in year 2. But look what happens if we're in a bad market. If we're in a bad market, the firm is going to lose 15 million in the first year and lose 10 million in the second year. So how do we solve for this? Assume that the project's cost of capital is 15%. So our discount rate is going to be 15%. And that the project's cost is 15 million. So our cash outflow, it's going to be 15 million. We're going to spend 15 million to invest in this project. And each year, a good market or a bad market is equally likely. In this example, we only have 2 states of the world. A state of the world is like a good or a bad. There's only 2 ways the world can be. And because they're equally likely, we know that the probability is going to be 50-50. So in part A, if the project is undertaken, what are the expected cash flows in year 0, 1, and 2? Notice how for cash flow in year 0, it's 15 million and there's no expectation operator. Because if it's a good year or a bad year, it doesn't matter. It's always going to cost us 15 million to take on this project. Let's look at our cash flow 1. Our expected cash flow 1, here we've got the probability of it being a good year. So that's 50% multiplied by how much we would get in that good year, the 20 million. And the same here if it's a bad year. We've got our 50% multiplied by how much we would get if it's a bad year. When we take the average across those values, that's our expected cash flow for year 1. And we'll do the same thing for year 2. We've got our 50%, our 0.5, multiplied by how much we get if it's a good year in year 2, and our 50% multiplied by how much we would get if it's a bad year in year 2, which is the negative 10 million. When we multiply our probability by our cash flow for that state and sum them up, we've got our expected cash flows. So on average, we're going to get 2.5 million in year 1, and on average, we're going to get 10 million in year 1. Notice how those averages are different from the actual cash flows we'll get if it's a good year or if it's a bad year, because we're taking an average across these cash flows. What is the NPV of the project? The NPV of the project is going to be that negative 15 plus the discounted expected cash flows across these states of the world. In this example, when we solve it, we get an NPV of negative 5.26 million. Should we take this project? No, we've got a negative NPV. What I want you to do is to solve if the project costs 10 million. If the project costs 10 million, should you take it or should you not? Our final concept is going to be amortization, which is paying back a loan. So you take out a loan for $1,000. It has a 10% annual rate. You'll pay it back over 3 years in 3 equal payments. We're going to set up a timeline, solve for the payments. We're going to apply the annuity formula, and lastly, construct an amortization table. So let's look at the timeline for these cash flows. Today, we borrowed $1,000. And over the next 3 years, we're going to pay that back plus interest. This looks so similar to an annuity formula, but what goes where? Well, first, those payments are going to be my cash flows. And I also know my present value. The present value is going to be 1,000. This is how much I got today for my loan. C, those are going to be my cash flows. That's going to be my payment. That's what I'm solving for. R is my interest rate. My interest rate in this example is 10% on my loan, and N is going to be 3. We'll be making 1 payment each year for 3 years. Looks really similar to what you did when you were solving for a 30-year mortgage, but it's a little bit of a different application. Okay. So we apply the annuity formula. When I plug everything in, on my left-hand side, I've got $1,000. That's the present value of the loan that I took out. On my right-hand side, I've got C divided by R multiplied by 1 minus 1 over 1 plus R to the N, all in parentheses. Okay, plugging things in and solving down, I find C equal to 402.1. And I hope you notice again that we're being mindful of the order of operations as we solve through. You always want to be careful about your order of operations. So C is going to equal 402.11. Meaning we're going to have 3 payments of 402 to pay off this loan plus interest. How does that work? Well, the interest declines as you pay down the loan. And hopefully this makes sense. You'll notice that we're paying the same amount every single payment, but a larger portion of that payment is going to the principal. So in year 1, when I borrowed my $1,000, I've got $100 in interest. I pay 402.11. 100 of that goes to the interest, and the remainder, the 302.11, goes to the balance. It's easier if we look at this in a table. So at the beginning of the year, I've got $1,000. I make a loan payment of 402. 100 goes to interest. 302 goes to principal. And at the end of the year, I've got 698. We do that again for year 2, and we do it again for year 3. And notice, magically, our loan payments with those 402 payments have paid off our loan plus interest. So we're going to end our time value of money lecture. We should be comfortable calculating the present value of cash flows if they're even and if they're uneven, meaning if it's the same amount every year or if it's a different amount every year. We should be very comfortable with an annuity and a perpetuity, growing and not growing annuities and perpetuities. We should be comfortable with NPV. We should be comfortable with amortizing loans. We want to be careful to apply the appropriate discount rate for our time periods. So quarterly for quarterly, annual for annual. You always want to make sure that your time periods match. And remember, the annuity and perpetuity are the present value of payments that start next period. So time T plus 1. For next week, we're going to jump into the role of financial managers and market efficiency. So make sure you read chapter 13, which kind of covers corporate governance. It talks a lot about the role of financial managers. And then also take a good look at chapter 6. It's going to be applied to risk and return. So that'll conclude it. And I look forward to our next lesson.